Hey guys, certainly miss seeing you guys around school, but I wanted to take a little bit of time to do a video over our last piece of information that I need to, last topic, material that I have to cover before we've exhausted all things on the AP exam and we get to start spending our time reviewing. So today's lesson will be over lesson 9.2, LHopitals Rule, and once again this is something that will be assessed on the AP exam, both AB and BC exam. So let's not waste any time. Let's get after it. All right. So our objectives in this lesson are that you would be able to understand what LHopitals Rule is and why we use it, when we use it, as well as we're going to look at a second form, a stronger form that can be used in repeated iterations. That'll make sense as we get into this. But really, the LHopitals Rule, to answer the part of, well, why do we use this, it's used to deal with what's called indeterminate forms of 0 divide 0 and infinity divide infinity. When we're trying to evaluate limits, if we just simply substitute and we get 0 divide 0 or infinity divide infinity, this is when we need to use LHopitals Rule. Okay? So, here's where they define that indeterminate form, 0 divide 0. Basically, they're saying if you've got two functions and both are 0 at x equals a, then the limit as x approaches a of the ratio of those two functions, it can't be found by just substituting because you'll get 0 divide 0, which is called a meaningless expression known as an indeterminate form. And note that it's called an indeterminate form. There are other indeterminate forms, as you saw in this list of objectives. Oh, and I wanted to say one other thing back here on these objectives is that you'll notice that two of those bullets are crossed out, and that's because the AP exam will not test you on the other indeterminate forms that are crossed out there. Our textbook does a great job going into further depth on other indeterminate forms, and lots of practice problems and examples are devoted to those other indeterminate forms, but I view this class being, obviously it's titled AP Calculus AB for a reason, to help prepare you for that AB exam, and so I'm just going to limit us to covering the material of these first two indeterminate forms, the two that will be assessed. All right, so what is LHopitals Rule? Here it is. LHopitals Rule says that suppose that f of a and g of a is 0, and that the derivative of f of a, the derivative of f evaluated at a and the derivative of g evaluated at a exists, and that the derivative of g at a is not 0. What does it tell us then LHopitals Rule is? It says to evaluate a limit where you get a 0 divide 0 situation, right? Because they just said that if I substitute right here, f of a and g of a is going to be 0. So if I'm trying to take a limit and I have a 0 divide 0 situation by substitution, well, what I can do instead is I can take the derivative of f at a, divide it by the derivative of g, the denominator expression, and evaluate it at a, provided this is not 0. Okay, so that's how I can apply LHopitals Rule. So let's see a practice problem. Here's our first practice problem. It says to use LHopitals Rule to find the limit. We go ahead and switch on over to the document camera, and we will do this. I highly recommend that in these situations where we look at some practice problems that you pause the video and give this a shot on your own, and then hit play and see how you did. All right. So, again, I want you to realize in every single one of these problems why I can't just evaluate this limit by substitution. If I plugged in 0, I have the square root of 4 minus 2, which is 2 minus 2, or 0 in the numerator. 0 obviously in the denominator, so that's a 0 over 0 indeterminate form. So we need to apply LHopitals Rule, which says go ahead and take, this will equal the limit as x approaches 0 of, take the derivative of that expression. Well, that expression, again, you have 4 plus x. I'm going to rewrite it just for the sake of making sure nobody gets lost. 4 plus x to the 1/2 minus 2 is what our numerator is. All right, so we haven't done the derivative yet, but here we go. The derivative, we can apply the power rule and the chain rule here. So this will equal the limit as x approaches 0. The power rule says 1/2 times the inner function 4 plus x to the subtract 1, negative 1/2. Times by the derivative of the inner function, but if you notice the derivative of the inner function is just 1, and then the derivative of this minus 2 is 0. All divide by the derivative of x, which is 1, so I really don't need to have a divide by anything. And now we just get to check by substitution, can I evaluate this limit now? And sure enough I can. You get 1/2 times 4 plus 0, or 4 to the negative 1/2. Keep in mind negative exponents belong downstairs, and rational exponents are really our radicals. So this is 1/2 times 1 over the square root of 4, and the square root of 4 is 2, so this is 1/2 times another half, or 1/4 is the answer to that limit. Okay, so that's how we apply LHopitals rule on a nice, decent limit problem. Now, LHopitals rule has a stronger form, however. Okay, and the stronger form, the main difference, it looks a little different, just all the verbiage at the start, but the main difference is, if we were to go back to the first form, it would just say that the limit as x approaches a of f of x over g of x, because these guys are going to be 0 if I just try to evaluate the limit by substitution. Okay, but the old form said, or the first form said, that this just equals f prime of a divide g prime of a. Well, this doesn't. This says it equals the limit as x approaches a of f prime of x divide g prime of x. So if this limit exists, I shouldn't say exists, but if this limit is able to be evaluated by substitution with plugging in a, then yes, this would just equal then f prime of a divide g prime of a, like the first form. But if it doesn't, this is allowing us to say, keep doing these limits of these derivatives. So potentially I might end up needing a second derivative of our original function up here that is going to end up working, divided by a second derivative of our denominator function in order to not have an indeterminate form of 0 divides 0 per se. Okay, so let's take a look at an example of LHopitals rule needing to use the stronger form. Here's one. I apologize for the notation not being as pretty there, but we're looking for the limit as x approaches 0 of 1 minus cosine x, all divided by x squared. So I'll switch on over to the .cam and let's try this one. Once again, a great time to pause the video and try it on your own. It's an opportunity for you to check for your own understanding. So there is our limit. So once again, see the need for LHopitals rule. Plug in 0, clearly your denominator is 0. Cosine of 0 is 1. 1 take away 1 is 0. So I get a 0 over 0 indeterminate form here again. So I need to take the limits as x approaches 0 using LHopitals rule. The derivative of the numerator, derivative of 1 is 0. Derivative of cosine is negative sine, but this is negative cosine, so this is going to end up being just sine, because negative of negative sine is sine, so sine x, all divided by the derivative of that denominator is 2x. Okay, and now let's check. Can I evaluate this by substitution? Well, what's sine at 0? Sine at 0 is 0. 2 times 0 is 0. I still have the indeterminate form 0 divides 0. Well, once again, this is an opportunity to apply LHopitals rule one more time. So this will equal the limit as x approaches 0, derivative of sine, cosine, derivative of 2x, 2. Now can we evaluate by substitution? Let's check. Let's substitute 0 in for x. Cosine of 0 is 1, and our denominator is a constant now, 2. So there is the limit as x approaches 0 of that expression, 1/2. All right. So this LHopitals rule, I don't have any notes necessarily per se on how it applies for one-sided limits, other than just to say LHopitals rule is not just defined for two-sided limits. It also applies for one-sided limits, and so we can do that as well, and we're going to see that here in this problem. Okay, so this problem asks us to evaluate the following limit using LHopitals rule, and this is a one-sided limit, a limit as x approaches 0 from the right of sine x over x squared. So once again, as now you can see it here, limit as x approaches 0 from the right, remember what that plus sign means, of sine x over x squared. So once again, let's check by substitution. Sine of 0 is 0, 0 squared is 0. So this is the indeterminate form 0 over 0 right here. So that's the need for LHopitals rule. So this will equal the limit as x approaches 0 from the right. Derivative of cosine, or sine, excuse me, I'm thinking ahead of myself, is cosine x. Derivative of x squared is 2x. This is sounded similar to the last problem we did, but it's not quite the same. And let's see what we get in this situation. Well, in this situation, if I were to substitute 0 in cosine of 0, what's the cosine at 0 radians? It is 1. Look at your denominator. It is 2 times 0, and that's 0. Well, is this the indeterminate form? The answer, no. It's not 0 divide 0. It's not, as we're going to look at here in a moment, infinity divide infinity. This is not our answer. We're not going to ever say 1 divide 0 because that does not exist as a number. However, we can think a little bit more about what does this expression approach as x approaches 0 from the right. As x approaches 0 from the right, this numerator is 1. Okay? But what happens here? Well, let's think about a really, really small positive, because we're approaching 0 from the right. So like 1 100th, okay? 1 100th. So if x is really 1 100th, 2 times 1 100th is 1 50th. Well, if I have a 1 50th in the denominator, that's the same thing as timesing or multiplying by 50. Well, if this is 1 times 50, this is now blowing up to 50. Okay, so what's really happening as x gets even closer and closer to 0 from the right than just 1 100th. We can get infinitesimally closer to 0 than just even 1 100th. Hopefully you can see where I'm going with this, is that this actually equals positive infinity. Now, once again, back when we talked about how limits are definite numbers, we could say that this limit does not exist, but the more appropriate answer is that the limit as x approaches 0 from the right is to say positive infinity, because that's what this expression is approaching as we're going that direction. Okay? So there's that example for you. I think that was a good one to take a look at. Let's get back to our PowerPoint, just mostly guiding myself here. Okay, let's take a look at an example with an indeterminate form of infinity divide infinity. Okay, so once again, this just means if I'm trying to evaluate this limit by substitution and I end up getting a rational expression of infinity divide infinity, then I need to also apply LHopitals rule. Notice this question is actually also asking for identifying the indeterminate form. That's what we should be doing at the start of every single one of these problems, by essentially checking by substitution to try to evaluate. And what we get in this problem is going to be infinity over infinity. The reason I know that is this is a limit as x approaches pi. And so if I think about cosecant, 1 over sine, sine at pi is 0. So I get 1 over 0 in the numerator, kind of like the last problem we just looked at and how we talked about how that's positive infinity. And likewise, in our denominator, you have 1 plus cotangent x. Well, cotangent also has sine in its denominator. And so with sine in its denominator, that denominator is going to go to 0, and you get something divided 0. That approaches infinity. Infinity plus 1, that whole denominator is approaching infinity. So that's why our indeterminate form here is infinity divide infinity. Okay, so having talked through that, let's go ahead and try to evaluate this limit using LHopitals rule. First off, both the numerator and denominator are technically not defined at pi, right? And so we could say that this expression is discontinuous at pi. And if you remember us talking about finding limits, discontinuities can give us some problems. What we're asked to find here is a two-sided limit. But the two-sided limit might not exist if we have a discontinuity of this value. And so that's why in this problem we really should look at finding our left-hand limit and our right-hand limit and then checking to see if they agree. Because remember, the definition of, or how we find a limit of a two-sided limit is the left-hand limit and the right-hand limit had to be the same thing. Okay, so in order for a two-sided limit to exist. All right, so with that said, let's go ahead and start by finding what is the limit as x approaches pi from the left. Okay, so as values get closer and closer to pi from below pi, so 3 to 3.1 to 3.14 to as we get closer and closer to pi. So the limit as x approaches pi from the left of this expression, cosecant x all over 1 plus cotangent x. I'm going to go right into doing the derivative of both of these. Maybe you guys have them memorized better than I do. It's something you should have down. The derivative of cosecant is negative cotangent x, cosecant x. The derivative of cotangent x is negative cosecant squared x. Okay? Now, anytime you're trying to evaluate limits and you have opportunities to simplify, please do. I notice a couple things right off the bat here. I've got a negative expression in our numerator and a negative in the denominator. Those go away. I've got a cosecant upstairs and I got a cosecant factor downstairs. So one of those cosecants is going to go away. So this is just on surface level, I feel like. The limit as x approaches pi from the left of cotangent x over cosecant x. Now, if you were to take this further and think about each of those two trigonometric expressions in terms of sine and cosine, cotangent, I'll write this out, the limit as x approaches pi from the left, cotangent's a cosine divided by a sine, and cosecant is a 1 over sine, right? When I have a fraction divided by a fraction, invert and multiply, and look what happens with those sine x's. They cancel, right? So we end up learning that this is the same thing as just the limit as x approaches pi from the left of just simply cosine x. Well, what does this equal? As x approaches pi from the left, I'm not saying from the left necessarily in the unit circle, I'm saying from the left in terms of numbers smaller than pi, I can evaluate that. I can substitute pi in this situation and I get negative 1. Right? Picture your unit circle if you're a little stumped right now. As x approaches pi from the left, so from smaller numbers, so that's me going this way, what's happening to my cosine value at all of these angles as I get closer and closer to pi? The value for cosine is getting closer and closer to negative 1. Now, likewise, I don't need to go through the whole proof. The limit, I'm getting off my page here, so let me go up here. The limit as x approaches pi from the right, it's still going to be, I didn't do any dealing with this left-hand limit until the very end, so now as I look at the right-hand limit, it's still going to be the limit as x approaches pi from the right of still cosine x. Well, this is just saying now, what happens as I approach pi from bigger numbers, from the side of bigger numbers. So that would be like if I was at bigger values, bigger angles, and getting closer and closer to pi, what's happening to cosine? It's also approaching negative 1. So if we notice, the left-hand limit, the right-hand limit are both negative 1, and so we can comfortably say the two-sided limit as x approaches pi of that expression is just negative 1. Right up there. Okay, so hopefully that helps. That is one example of a indeterminate form of infinity divide infinity. Okay, I've got one other example that I want to look at with you guys that I think will be helpful. I think there's a couple in your homework assignment that are going to be like this with logarithms, and I wanted to show you this little trick that you're going to see in here. So again, it says identify the indeterminate form and evaluate the limit using LHopitals Rule. If you were to try to evaluate by substitution, the natural log of infinity plus 1, so infinity, right? The natural log of infinity, well, e to what power makes infinity? Infinity, right? E to the biggest thing you can think of. Okay, so the numerator is infinity, and the denominator log base 2 of infinity. So this time, 2 to what power makes infinity? Well, infinity, right? So this is infinity over infinity indeterminate form as well. So let's switch on over to the doc cam here, and let's take a look at this problem together. What's going to be most helpful in these problems where we're doing the limits and where we're dealing with logarithms here is to get our logarithms being the same logarithms. So we're going to go ahead to start on this problem. We're going to use the change of base formula. If you can't remember the change of base formula, it says something like this. If I have log base b of a, but this equals log base c, whatever I want to choose, of a divided by log base c of b. Okay, so that was change of base rule and logarithms that we learned last year in pre-calculus that we're going to put to use here. Okay, so this equals the limit as x approaches infinity of the natural log, I'm going to leave that as is, natural log of x plus 1, all divided by, I'm going to choose to rewrite this in terms of natural logs. So this would be the log base e, or natural log of x, divide the natural log of 2. Okay, so when I go ahead and do that division, I really end up getting this, the limits as x approaches infinity of that natural log 2 comes out at the front here, and I get the natural log of x plus 1 all divided by the natural log of x. Okay, so remember your properties with limits. If you have a constant factor that you are taking a limit of, that constant factor can come out front. So we have, this is the natural log of 2 times the limits. These natural logs and limits are giving me fits when I'm writing them. As x approaches 0, of this expression, the natural log of x plus 1 divided by the natural log of x. Now, this hasn't helped me get rid of my indeterminate form at all. I haven't actually applied LHopitals Rule at all yet. So this is still the indeterminate form infinity over infinity. So I still need to do LHopitals Rule. Okay, so I'm going to go ahead and do that. So this will be the natural log of 2 times the limits as x approaches 0. The derivative of natural log is 1 over. Applying the chain rule here, though, in this situation, the derivative of the inner function is just 1, so that's fine. All divided by the derivative of the natural log of x is just 1 over x. Okay, I'm running out of a little bit of room, so let's go on up here. And so we're going to have the natural log of 2. Okay, so I'm just going to clean up this complex fraction times the limit as x approaches 0 of, anytime you have a fraction divided by a fraction, invert and multiply. And so we get x over x plus 1. Oh, and we had actually infinity, not 0. I apologize on that. Some of you probably caught that already. This was the limit as x approaches infinity on all of these. So needed to make that change. Okay. Now, here I run into some problems where I can't necessarily, if I plug in infinity right now, I get infinity over infinity still here. So if I wanted, I can go ahead and do LHopitals Rule once more. So let's do that even. So this equals the natural log 2 times the limit as x approaches infinity of, what's the derivative of that numerator? 1. What's the derivative of that denominator? 1. So this is the natural log of 2 times the limit as x approaches infinity of 1. Well, 1 is a constant function, so it's not dependent on x, it's always going to be 1. So it sure looks like this is just the natural log of 2 times 1, or the natural log of 2. Okay, so what do I learn from this? I learned that the limit of this logarithmic rational expression is just the natural log of 2. That's kind of a fun problem right there. Okay? So that kind of concludes this lesson, lesson 9.2. It's a relatively long assignment, but I'm giving you plenty of time. So don't feel like you've got to get after this and do this all today, tonight. Again, I realize you guys are juggling, some of you 6, some of you 7 classes, and this getting used to this whole distance digital learning thing is not easy. So this is why I haven't been bombarding you with a lot of stuff at this point. I want you to try to get yourself organized with how school's going to look, because it's a new norm for you as to what school's going to look like. So anyways, this is lesson 9.2. There's the assignment. Again, this work won't be due until Friday at 8 a.m. And you can submit it to me by either email or, probably better yet, through Remind. So anyways, I hope this makes sense. As always, send me messages if you need help with anything. I can take some time to shoot another video out to you guys or help in some way. So once again, I miss you guys and hope this video finds you all well, and take care, and can't wait to see you next time.